perfect model for the future. And yet we still are trying to use data to predict the future. And this doesn't really make a lot of sense. And in philosophy, this is known as the problem of induction. It's famously phrased by David Hume as a thought experiment, which is, how many times must we observe the sun rise to be certain that it will rise again tomorrow? You feel this deep sinking feeling in your stomach? That's what philosophy feels like, right? So, okay, you're fairly certain the sun is going to rise again tomorrow, but are you really certain? And how many more times would you have to observe it to be 100% certain that it's going to rise again tomorrow? Now, you might be immediately tempted to go think about the science and what we know, and that maybe someday the sun will explode. And you say, well, you don't know. Like, I don't know what's going to happen tomorrow. And that's the point, is that there isn't any amount of evidence, any amount of data that you could ever collect on the past that could really predict the future. Even something as certain and so normal in our daily life is that the sun will rise again tomorrow. So that feels like we're not starting off at a good point here, right? So how do we use data? And how do we get past this problem? Well, we have to make an assumption. We make an assumption that our universe is governed by rules. And these rules can be used, as we know them now, to predict outcomes that will occur in the future. And if you assume that our universe has rules, then you can use a process called deduction or formal logic to take these rules and predict what will again happen in the future. So a rule might be, force equals mass times acceleration. Or a rule might be, people in France tend to speak French. That might be a rule as well. But there are rules that govern the way that our universe as we know it works. And we can use those rules to make predictions about the future. But sometimes we don't know what those rules are. And that's where data comes in. That's history. These are things that you can measure, things about the past. And we assume that the rules that will apply tomorrow also applied in the past. And so you can use a process called induction or inference to take things you know from history and apply them to a rule. And once you have that rule, and you can also think of it as a model, but in this case, let's think about more broadly as a rule, to use formal logic, deduction, to predict outcomes. If there's one thing you take away from this talk, you're going to learn that deduction is great. Logic is like a very solid foundation, but induction and inference is a very, very weak form of logic that you can break very, very easily. As a brief input, where does data fall into this? It falls in because we have data about history. And often we have data about now, which I think of as initial conditions. And that's often very useful. So there's two places where data can fit into this process. But it's actually not useful for the actual predicting the future part, right? Data is useful from history to rules about how our universe is governed. Okay, we're moving on to part 2 of the talk, where we talk about how weak inference and induction really is. And we're going to talk about this assumption that there are rules that govern our universe. If you don't make that assumption, what is the other alternative? It's that everything is random. That our universe is entirely stochastic and just based on chance. So at the end of the day, what are you trying to do in the process of inference? You're trying to ask the question, first, is a rule necessary to explain the data that I have? And if it is, or is chance sufficient? Can I explain this data by chance alone? And if a rule is required, what is that rule? And once I know that rule, then I can go predict in the future, which is what we all want to do in the first place. So that all of this boils down to your model of chance. And what do you consider chance? And let's talk about that for a second. So one of the things about evidence and data from evidence is that our ability to infer from data is that we have to say what we observed is unlikely to occur due to chance alone. Therefore, a rule is necessary. But that what unlikely to occur due to chance looks like depends on a lot of things. In fact, it depends on almost everything. So let me give you an example of this. This is a classic data problem, entity resolution, where you're tasked with 2 pieces of data, or let's say 2 documents here, and you're supposed to ask the question, do these refer to the same person? So let's pretend, for example, that you work at a small startup, and there are 5 people and 4 of them are girls, and one of them is named Jason. And you look at this data, and you say you have one piece of paper that says Jason in Crystal City is a data scientist and a phone number. You have another piece of paper that's in your office that you were looking at that says Jason R, who's in Arlington, is a data analyst and another phone number. And you're at this startup, and so you know that you recently moved offices. And you want to decide what is the chance that these refer to the same people. Well, your model of chance, being that 2 pieces of paper that have in your office both say Jason on them and do not refer to that one Jason, the only one that exists in your universe, is probably fairly low. These 2 documents probably refer to the same person. But we can play a different game. Now, you're not at a startup. Let's say you are organizing a meetup across all of the DC metro area, for example. And you have people who have signed up for your meetup or for your seminar, and your database gets corrupted. And now you're trying to decide, okay, is this person who signed up Jason and Jason are they the same person, or are they 2 different people that I need to account for? And you might say, well, Crystal City and Arlington are 2 different cities, but they are often interchanged. Sometimes people go back and forth, and it's possible that Jason moved from one place to another. And they both have similar job titles, and they both have similar phone numbers. And the one thing I know is that in this database, all of these phone numbers were typed in by hand. And you know what happens when people type in phone numbers by hand? Mistakes. And one of the things you notice is that these phone numbers are very similar, and all they've done is flipped 2 numbers. And so really, this person is probably more likely the same person, because these are enough evidence that it probably refers to the same person. But we can play this game again. Now, you're not organizing a local meetup, you're organizing a nationwide or international organization. Your database gets corrupted, and you want to decide, is this enough evidence to decide that these 2 documents are related to the same person? Now, you know that you would think Jason is a very, very common name. Lots of people are named Jason. Lots of people live in Arlington, and lots of Jasons live in Arlington and in Crystal City. Lots of people are data analysis, and there are a lot of phone numbers that differ by only 2 digits in my giant database. So if I were to use this as a rule, as sufficient evidence to decide that documents are the same across my entire database, I would make a lot of mistakes. And so I'm going to have to decide that these are 2 separate people. One of the key things that you learn from this is that the context is everything. Your model of chance is everything. And the data is a very, very small part of that. And in fact, this data didn't change at all. One of the things that I find very frustrating is when someone will tell you the data speaks for itself. The data never speaks for itself. It never, ever, ever speaks for itself. In fact, from a philosophical level, it is impossible for it to speak for itself. Because the only way for it to speak is for you to have a model of chance, some context around how the data was collected, when it was collected, why it was collected. The questions of how domain specific go very much into the context in which your data was collected. And so data depends on everything, and that is extremely frustrating, because you can't just take the same data, move it to another place, and make it the same inference. Okay, there's another way in which inference is very, very weak. And again, it comes back to this idea that inference is related to chance, about understanding what unlikely really means. And so you're asking again this question, is chance sufficient to explain my data? Do I need a rule to explain my data? And if I need a rule, what is that rule? Here's the thing about chance. Things that are unlikely to occur happen all the time. In your life, I guarantee you something has happened that was extremely unlikely, but it happened to you, and that's because the more you look for things that are unlikely to happen, or the more chances you give something unlikely to happen to occur, the more likely it is that something will occur. This is the classic statistics problems of flipping a coin, right? How unlikely is it to flip 10 heads in a row? Extremely unlikely. But how likely is it that if you flip a coin infinitely for the next 10 years, that at one point you get 10 heads in a row? It's almost 1. That matters. And it matters for the way that you interact as a data scientist and with your data in the world. There's a famous thought experiment, philosophical thought experiment for this too. And it is framed as the concept of a monkey on a typewriter. And it goes like this. If there's a monkey on a typewriter and you see it banging along, and then you look at the sheet that is coming out, and it is typed word for word the Iliad. you would think, wow, this is one special monkey. Like, there is no way that that monkey is banging on these keys by chance and writing out the Iliad. Something weird is going on. I need a rule to explain it, and this rule is probably going to be that this monkey is an incarnation of some sort of past body. But that depends, of course, on how many monkeys. Because if you, again, now, if someone only told you there was one monkey, that would be very surprising. But if what you didn't know was at the same time, in every room in the universe, there's another monkey banging on keyboards and typing things, that the chance that one of them types the Iliad, or if you don't have very strict definitions of what you're looking for, let's just say a sonnet or a haiku, or really just a one line from Shakespeare, to be or not to be, at any point. If you have no strict definition of what it is you're looking for, and how many times you've looked for it, and how many different ways you've tried, then your data means nothing whatsoever, if you don't have complete control over how many times you looked. This ends up being a major problem in science right now, and specifically in biological science, because a bunch of people can perform the same experiment over and over and over again, and only one of them will observe something that is unlikely to recur due to chance alone. All of the rest of them will not see it, but that one study will be the only one that gets published. And that is a problem, because then looking back, the body of literature in which we've created is extremely unreliable. And this is something that science, and especially my field of science, where I was in neuroscience and biology, is learning the hard way, really, really hard way right now. And it's something that I think in data science and in automated learning, we're going to learn the hard way very, very soon. Because one of the things, one more picture, one of the things that you might not think about when you're using a machine learning, in particular something like a random forest algorithm, is that this process of iterating the same thing over and over and over again on the same data, this is what your algorithm is doing to try to find your answer. And that's a problem. It's also the cause of overfitting as a concept, as a philosophical concept, the cause of overfitting. So when we come to that, inference is very, very weak. There are many more ways in which inference is weak. I had a lot of time to think about this in grad school, and I'm only going to go over two of them, those two right now. And the two biggest one is that chance is subjective. Your model of normal, your context, it depends on literally everything about how you framed your problem. And that leads to the really hard questions that no one has answers to. And to make that problem worse, the harder you try to find evidence, and the more iterations you make on your model, the less likely your model is to reflect a true rule. So the more you beat your data, the more months you spend trying to make it work, the more likely you're fitting a rule, you're overfitting into something that doesn't exist. Because there always is the possibility that there isn't a rule that explains your data, that your data is always explained better by chance. Chance, that's the big thing. What does this mean for us in real life? Well, here are some ways to do some optimal inference strategies. Control the entire context around the way the data was created. Make one specific prediction. Consider only one feature, variable, or predictor at a time. Never reuse the same data for a different analysis. And if your prediction does not sufficiently explain the resulting data, start over. New data, new experiment, new context. If this sounds familiar, it's because it's the scientific method. And the scientific method exists for a reason. Okay, if it was possible to replace science with machine learning, I guarantee you all the people trying to cure cancer right now would be all over that, right? And that's one of the ways in which when people tell you to do magic with data, let's say, you have to be able to understand whether your problem can actually be solved by the approaches in which you're looking to do it, or whether really you've reached the foundation of science in and of itself. So let's talk about when data science has won, and what is different between these things. One of the classic examples that you'll learn in a beginning data science class is the question of deciding between different numbers and having a machine decide which number is chosen. One of the things you should realize about this problem when you look at it is that you don't have to make the assumption that a rule exists to explain this data. And that's really important because we created the rule. We decided what language was. And so someone can't write the number 1 and tell you that it's a 9, right? There are rules that exist and you don't have to assume that. And that's a really good and strong starting point for a problem that is solvable by data. is rules that humans have created. And something like, this is a 1 and this is a 9, there's not a lot of debate about. People might write them poorly sometimes, but that's just noise in your measurements. The concept of 1 and the concept of 9 is something that we all agree on. Or if we don't, then we have bigger problems on our hands. So this is a problem that can be solved fairly well with traditional machine learning and data science. I did not change this since the last time I gave this talk, but at the time I was giving election predictions as another fantastic data science win. And that's when we come back and we learn yet again that the history can be at times a very poor predictor of the future, and that is a problem. But at the end of the day, predicting election results and polling is actually something that data is really good at, on the scale of bad to good at which data works. And one of the reasons is, like, our definition of what counts as winning in an election is very clear. 1 person, 1 vote. Like, in these states, 50% wins. Like, it's only down to just measuring the variability of this concept in which a lot of rules apply, and that we know these rules are true because we created them. Another great example of what I consider data science wins are traffic predictions. And again, the thing that makes these problems good for data and good for data scientists is that we decided what traffic patterns look like. We decided you can only drive on roads, or really most of the time we only care about driving on roads. We decided that one car couldn't drive over another car. We decided that there were speed limits and different speed limits on different roads that are, more or less applied. So there's some rule that we can use to start normalizing this data. And since we know these rules exist because we created them, we can do a really good job solving this problem. Another way in which you can win at data science is by having weak rules, but having the consequences of failure be very, very low. So for example, a recommendation engine. How many of you have ever been recommended something on Netflix that you didn't want to watch? Right? But sometimes they win, and the wins are bigger than as far as cost than the losing, and so it ends up being okay. So you have weak rules, and the weak rules end up being people who like this probably are similar in a lot of ways as these other people, so let's group them together and we can make these predictions. And that works fairly well. You can argue with me, but it works fairly well, in part because failure has a very low cost. But that doesn't work as well in fields that I used to be in, like when you're trying to tell if someone has cancer or not. Then the cost of failure is much higher, and this ends up being a much bigger problem. So again, this is the method for how data works. You have to know what the rule is and use the rule to predict the future. If you have to make the assumption that a rule exists, then you're in the concept of pure science, and you're in for a very hard and long process that takes a very long time. Data will work in systems in which humans have created the rules. And the more that you can rely on rules that you already know about, in other words, the more you can use domain expertise to solve your problem, the better off you're going to be at making a successful data science, data solution to a given problem. Yes, so repeating myself slightly here, inference is not a strong tool. It is very easy to break. In fact, you can break it just by doing it too often. Knowing rules is always better, and acknowledge that don't be a monkey on a typewriter. Please do not do 50,000 grid searches. Understand that that is the way to make a model look like it's working and very unlikely to generalize. And acknowledge that no amount of data can predict things that are inherently stochastic. If you have a system that is primarily designed by randomness or noise, which a lot of things are, you will never win. And no matter how many times your boss asks you to make a model that predicts insert this other thing in whatever it is in the future, the answer should be no, that's not how data works. Data is not magic. And that is it. Any questions? Comments, concerns, arguing philosophy? Yeah.
I'm sorry, I have to ask a silly question. I missed your name.
Oh, sorry. Clare. Clare, yeah.
Claire.
Gollnick, sorry.
Gollnick.
Yes, you can come talk to me afterwards. We can talk about more things. Yeah.
What's a good example of data that doesn't work? Like the kind
So it's always, because it depends on everything, it depends on the exact question you're asking. But something that I would say that's not well defined by rules, well, okay, I'll give a very good example and then I will give a less good example. And that's really just a question of how hard the problem is. Cancer is a disease that is caused by entropy. It's caused by random mutations in your DNA. And again, this is my example, obviously, because of my background. But we will never have a model that predicts who is going to get cancer. The best we're going to do is predict types of people that are more likely to get cancer. And that's because the fundamental causes of cancer are random mutations that are really down to the molecular level. So this kind of gets into it depends at what level of abstraction you need to solve your problem. So sometimes knowing high risk groups is good enough, and that's helpful in your outcome, even if you haven't entirely solved the problem. Another one that I would say is fun, like I have human interactions, social networking, predicting how and where people will interact or what they will do next. Terrorism, predicting terrorism is a really great example. That is a thing that is much more stochastic than we like to believe. Many people or any sort of violent crime, people with the same conditions, almost everything you can measure, some become violent and some don't, and we don't know what it is that causes that, and that tends to be. So you'll find if someone is asking you to solve problems like that, unless they're paying you a ton of money and giving you a ton of time, it's not going to happen. Yeah?
Can you define the random experiment?
The random experiment?
Yeah. What is the random experiment?
I'm not sure where I said random experiment. In general, when you talk about an experiment, when I think of it, is that like in a lab where you are controlling everything you possibly can. You're going to great lengths to have a control group A, control group B, and an experimental group. And then you're only making those comparisons between when you've made every effort to control that. And even then, there are problems that can be caused in inference, but that would be the best type of experiment that you could run.
Yeah, but I think the random experiment is a very important concept in probability statistics.
Oh, yeah.
And the random experiment, the random means you never know about the future. So it's a random.
Yeah, but you can't.
Yeah, but why we care about this kind of a random experiment in the probability statistics? Simply because in the long run, we can identify some kind of pattern. Still, we don't know. It's about the random. So the statistics is all about probability and then how to quantify the probability using the specific theory and distribution.
Right, but your definition of random changes based on everything, right? So that's the problem, is there's no concept of random that's independent of assumptions.
No.
So for example, people always ask, you flip a coin, what is the chance you get heads? People will say 50%, but I didn't tell you how many sides my coin has. You're making an assumption in order and those are rules that you're implying on your system in order to have a concept of randomness. And that's why it's really a question of philosophy and not statistics, because in every statistical model of randomness, there are assumptions about how the world works, how many options are possible, over what time scales, whether it's discrete or continuous, whether the signal you're measuring has noise. All of these things are assumptions you build into your model of randomness, and that is the foundation of statistics. So there isn't a way to model true randomness at a pure philosophical level. You have to make some sort of assumptions.
I have some different ideas as a statistician.
You can, but you're going to have to argue with the philosophers on that one. I have met more than a few statisticians who feel that way. But you should definitely, I can recommend some books. Yeah.
So you said data should never be reused, and I can see the logic behind that. But I'm also wondering, there's this sort of movement towards open science and open data, and a lot of the reason for that is that there are times that data can be used that was gathered for one reason and it has use for others. What do you have to say about that?
I was choosing my words carefully. The optimal inference strategy, if you were to try to be perfect in every way, which is not an achievable thing to do, is to never reuse data. So that's, again, a philosophical argument that is abstracted from reality. In reality, you reuse data for good reasons. You just have to understand that hitting the same data with the same question over and over and over again is problematic because of this. Our definition of evidence is defined relative to chance.
So, given that logic, it almost seems though that hitting the same data with a different question might actually be.
But except that you haven't controlled the context, right? Because the context determines what questions can be answered. And so you have two options. You have an experiment with the open data where a person has designed this data and collected it in a controlled environment that is being controlled for one specific question and is not controlled for whatever concept of question that you might be answering. Or you have data that's on history, in which case you run into the problem of history doesn't predict the future. And you don't know if the thing you're measuring has changed or not. So yeah, I don't, in philosophy, as we discussed, and in the baseline level of statistics, you operate in this world in which you can live in these optimal or perfect worlds, and that's just not, that's not reality. So that was a great question. Okay, yeah?
I was just curious if you're gonna update your election win to talk about alternative facts?
Yeah. I'm gonna have to explain go all the way to the Popperian theory of what is truth. And if you observed it with your own eyes, is it still true? I don't know. Or the philosophers have not decided if that's sufficient evidence.
Then you have to kind of know like eyewitness testimony and like what is observing it.
Yeah.
My mom's an psychologist.
Yeah, yeah. So that's, and if you're interested in that, Karl Popper is one of the best places to go as far as beginnings of statistical theory, and as well as the foundations of knowledge as a good book to start with. Okay, you can definitely, if you want to argue about the philosophy and the statistics, I'm all for it. We can do it. Come find me afterwards.